Dear friends, welcome to this particular session of lecture on methane gas hydrate. In this particular topic, we'll be covering four different aspects divided into four different modules. The modules are Introduction to Methane Hydrate. It consists of composition, structure, genesis, basic biogeochemistry, purpose of methane hydrate research, stability diagram of methane hydrate. In subsequent modules, we will see the present and past seabed methane seepage events, methane hydrate exploration, and methane hydrate exploitation. When we talk about methane hydrate, let us first see what is called gas hydrate. A gas hydrate is nothing but a combination of water and gas molecule in a crystalline structure, which is normally stable at a very high pressure and low temperature. For example, here you can see that you have a crystalline structure in which you have water molecules forming a cage-like structure, which is also known as clathrates, within which there is a host molecule. The host molecule is a water molecule, and there is a guest molecule. This guest molecule, if we say methane, then we can call it as a methane hydrate. You can see by definition, a crystalline solid consisting of gas molecules, normally methane, each surrounded by cage of water molecules. On dissociation, 1 unit of gas hydrate produces nearly 164 unit of methane gas and about 0.8 unit of water at standard temperature and pressure conditions. You can see in this volume diagram also, you can have 1 meter cube of hydrate, say methane hydrate. At standard temperature pressure condition, it will be a 164 meter cube of gas and 0.8 meter cube of fresh water. So you can here also you can see that these are the different clathrates units within which you have the methane molecules as the guest molecules. So there is a host molecule, which is the cage structure of water molecule, and within which you have the guest molecule or the methane molecule. Now, when we talk about methane hydrate, you will be wondering that how the methane hydrates actually look like. These are the different pictures of methane hydrates which are been recovered from the Indian EEZs and from other regions too. You can see here this is called a nodular type gas hydrate, and this is a typical fracture filling hydrate. Here also you have a typical fracture filling hydrate. This is called a vein type, thick vein type hydrate. And here you have this within the pebbles and within the small granules, you have got this pore region which are filled with this white material are the hydrates. Now, what are the darker material? The darker materials are nothing but the marine sediments, which are composed primarily of clay, silt, and sand. Here, these dark materials are composed of pebbles and cobbles and granules and sand. These kinds of material form a very nice porous structure from which, and also a much greater permeability, from which people are trying to do the exploitation more and more. Now, when I say crystalline structure, how do we know that it is a crystalline structure? One, we can look at the electron microscopic diagram photo image, which is a very high magnified image of the methane crystals, and you can see here that there are nicely developed crystalline faces, which is a typical of a crystalline structure. Further, we can understand about the crystallinity by studying the X-ray diffractometry. By X-ray diffraction, you can see there are different peaks, and each of these peaks represent a crystal lattice structure or the different faces. So these two things proves that the methane hydrates or the gas hydrates as such are well crystalline material. And you can see here there are the different kinds of combination of the guest molecules like methane, ethane, carbon dioxide, or propane, isobutane, methane, neohexane, methane, cyclopentane. These kinds of different kinds of, if you change the gas molecule as or the host guest molecule, the structure changes. That is why in methane hydrates we can see there is a structure 1, there is a structure 2, and the structure H. They all have different combinations of the guest molecules. Now, when we talk about the methane hydrate, you will be wondering that where they actually occur and why they occur. That is why where methane hydrates occur and why. You can see all along the continental shelves, you have all the gas hydrate that is recovered and gas hydrate that is inferred. That means the regions where further exploration can be carried out for the discovery of the gas hydrates. Now question is why these gas hydrate reserves or the deposits have been recovered or inferred from these shelf regions, shelf and slope regions. The reason is that if you look at the global organic carbon burial map, then you can see that in these regions only you have the maximum deposit of organic matter. So these organic matters constitute the main raw material for the synthesis or the formation of the methane gas in the sediments and subsequent formation of the methane hydrates. Now, when we talk about genesis of methane in the sediment, we have to understand there are two main modes of genesis. One is the microbially generated process or called microbial methane gas. Another is known as the thermally generated or catagenically generated methane gas. In this particular diagram where we call it the basic sediment biogeochemistry and methanogenesis or methanotrophy, you can see that below the seafloor, as we go down, certain processes are happening. The sulfate ion concentration in the sediment fluid are decreasing, whereas from here we can see there is an increase in the methane concentration. There is also an increase in the alkalinity concentration in the sediment. You can see the same thing happening here also in this particular. All these things kind of analysis are carried out in the sediment cores which are collected from the seabed. Here also you can see that the sulfate concentration is decreasing, methane concentration is increasing, alkalinity is increasing. All these processes, these basic biogeochemical processes which are microbially driven process or enzymatically driven process, can be represented by simple equations which shows that how the sulfate concentration changes and hydrogen sulfide is produced, how the sulfate concentration drops, how the sulfate and methane reacts, a production of hydrogen sulfide and bicarbonates. Now, where the sulfate concentration and the methane concentration intersects, we call it as a sulfate methane transition zone. In my next module, you will learn more about the sulfate methane transition zone and what kind of processes happen there. Now, I just said earlier that we have a biogenic methane and a thermogenic methane source. Now, when you say biogenic methane and thermogenic methane we saw in the earlier slide, how they are forming. You have the organic matter, then there is a microbially mediated enzymatic breakdown of the organic matter, which is also known as the fermentation, which produces simple organic molecules, which are the food for the methanogens, which are the bacteria which can produce the methane. So there are two main processes we call as acetoclastic methanogenesis and as a hydrogenotrophic. Acetoclastic methanogenesis is represented by such kind of an equation, whereas carbon dioxide and hydrogen, which is called hydrogenotrophic methanogenesis, are represented by such kind of equations. Now, on the other hand, in case of the thermogenic methane gas, you can see that they are formed at the very deep in the oil-related gases, also known as the oil-related gases, because of the catagenic process at a high temperature of 120-130 degrees centigrade temperature at a deep burial depth of 2 to 3 kilometers below the sea floor. You can see that the methane gas is generated and then it can move upward through the permeability, using the permeability in the sedimentary formation. And when they can leak into the seabed or they come very close to the seabed, whereby they form the hydrate deposits. Now, how do you understand or distinguish between a thermogenic gas and a microbially generated gas? By using certain isotope ratio numbers like carbon isotope ratio number, which is a ratio of carbon 13 and carbon 12, or the deuterium by hydrogen isotope ratios. By using these kinds of diagrams, we can easily distinguish the origin of the methane, whether it is biogenic methane or it is a thermogenic methane. Now, I said that the methane hydrate is stable at a high pressure and at low temperature. So how do we show it diagrammatically? Diagrammatically, it is shown by a drawing called the phase diagram, where you can see this is the phase and this is the thermal gradient. And you can see that this temperature curve and here is a thermal gradient. And you can see that here in this zone, the hydrate is stable, because the temperature and pressure condition here is perfect for the stability. But below this zone, we can see that the production of gases. So this boundary between the gas hydrate where it is stable and the where lot of extra gas is produced, this is known as the base of the gas hydrate stability zone. Now the thickness of the stability zone, amount of methane hydrate there, depending on the temperature pressure condition as well as the flux of methane that is coming from either from the biogenetically generated or from the thermogenically generated. Now, from the Indian point of view, we can see that the lot of methane hydrate we have found in the Krishna Godavari basin, in the Mahanadi basin, and there is some prospect in this particular region, and also in the Andaman basin. So in these regions, the exploration work is still going on, and we have already found a lot of methane hydrate there. Now, if you look from the global perspective, you can see that methane hydrates can be seen in many different places here. Each of these circles represents the approximate resource potential that is in trillion cubic meter. Now, you can see in the Indian region, in the Indian shelves, it is approximately 2 trillion cubic meter, which is of course not the absolute numbers, because these numbers entirely depends on the extent of exploration, the quantification of many different complex aspects of it. Now, we have seen that gas hydrates or methane hydrates can be present within the fracture zone and also within the granules and the sand pore spaces. So there is a lot of research going on what kind of lithologies one should target for a economically viable exploitation. So we have found that although there is a huge reserve of methane hydrate globally, but this region A, which is mostly are sandy and porous material with a lot of permeability, they are good for the exploitation purpose, so that there is an unhindered flow of gas through this region. And such kind of the testing has already been carried out in the Nankai Trough in Japan, and also in the Malik Well in the Canada region, in the northern Canada. However, these are still in the research regime because a lot of work needs to be done for an economically viable program. Now, what is the purpose of methane hydrate research? We can see that there is an energy resource, there is a seafloor instability or the hazard mapping, there is a global warming issue, and there is a benthic biology issue. Of this, the benthic biology issue I shall be covering in the next module. When you say energy reserve, you can look at from the Indian perspective mainly, you can look at the very small amount of energy reserve that India has. We have very little compared to other oil-rich countries, we have very little. But if you look at our total consumption, India imports 80% of its total domestic consumption of hydrocarbon. So that naturally puts a lot of pressure on us for more and more exploration and exploitation of alternative hydrocarbon resources, of which methane hydrate is a very important hydrocarbon resource. And since we have a lot of them in our offshore region, so it is important that we explore and exploit them. Now you can look into this graph and say that how much is our production and how much is our consumption. As I repeat here, that India imports more than 80% of a total hydrocarbon consumption. Now, methane hydrate is also a very clean energy resource. You can see compared to the petroleum products or compared to the normal petroleum thing we use, you can see that the oxidation of methane produces only carbon dioxide and nothing else. So this is a clean fuel, and you can see the global distribution of this. You can see the global distribution. You have the gas hydrate in terms of gigaton of carbon. In terms of gigaton carbon, you can see it's a very huge reserve. But as we see in the previous slide, that one need to understand which kind of lithology the gas hydrates are stored and what is the economically viable way of exploiting the hydrate or the methane from that particular kind of lithology. So here you can see that why it is a clean energy. You can see how much amount of the hydrogen by carbon ratio is very high, 4:1, which is a very important parameter to define something as a good energy reserve. you can see that the amount of kilojoule per gram of energy produced is 51, which is quite high and higher than others. Amount of carbon dioxide produced is only 1 mole, and so it's a very clean energy reserve. So it produces lot of heat, lot of energy, but does not produce any other pollutants except the carbon dioxide. So this is the second part where we are talking about why why should study the methane hydrate. You can also see that the thawing of methane hydrate, which is very shallow, let us say 200, 300 meter or 100 meter below the sea floor, if there is a thawing of the methane hydrate, it can cause a landslide, it can cause a instability, which is extremely important from the point of view of oil rigs, oil pipelines, which needs a stable seaflow. So there is no landslides and other processes which can cause a lot of economic loss. You can see here in the Krishna Godavari basin itself, there are evidence of landslides and slumping, which we relate with the possible thawing of the hydrate and the gas flows causing a instability. This is the final slide of this particular module, where we can see that methane hydrate should also be studied from the global warming point of view. Why? Because methane hydrate is at least 20 times stronger greenhouse gas than the carbon dioxide. You can see that through the industrial revolution process, how the carbon dioxide has increased. But you can also see that how the methane concentration has increased, this particular green curve. So we need to study that how the methane fluxes are from the seabed and from the other wetland regions, because this is a very important global warming gas, and how they are consumed by different biogeochemical processes also in the sediment, which reduces the flux of the methane from the seabed. With this, I end the first module. In the next module, we shall be studying more on the benthic biology and the cold ships. Thank you.